we're going to have a short quiz, okay? Yeah. All right, folks, we got 2 more minutes. I feel really cold. I got a jacket. Okay, let's have 2 more minutes and we begin today's lecture. Okay, everybody is ready? Almost finishing up the quiz? You can pass to the left side to your classmate, then I'll collect them at the side, okay? Then we can begin today's lecture. And don't forget to write down your name. I have. See, occasionally some of you forget about that. Okay, thank you, everybody. Perfect. I'll certainly grade it. And so, today, we gonna be very excited to present to everybody the latest finding of how we can combine osmotic pressure and the Flory-Hagen theory for the phase behavior. As I said, this probably is one of the most exciting part of the chapter 7 of your textbook. Is about how we can use this to predict your material's property. So I left a question for everybody to think about in the last part of the lecture is A2 and Chi is long lost brothers? Are they basically talking about the same problem? Is there anyone had any answers or guess? Have any? If not, let's chat a little bit about that. So what is we discussed A2? A2 is the second viral coefficient. We talked about in the last lecture about how we can use a plot of osmotic pressure divided by CRT. C is concentration, R is gas constant, T is temperature, to get what is the molecular weight as well as the A2 parameter. And we showed a couple examples of polystyrene dissolved in cyclohexane, how you can get A2s to be negative, equal to 0, or positive, right? So that tells you A2 equal to 0, as we define. There's no interactions between energy exchange, so we can say this is equivalent to a Seda solvent. What about the other part? So the other part is we know in the Flory-Hagen series, as well as the recently, we define thermodynamics of what is chemical potential can be also get from free energy G. We can use the following relationship to connect chemical potential with the Flory-Hagen theory. This everybody should be familiar with. Is a generic form of Flory-Hagen theory. And chemical potential is nothing but partial derivative of free energy to molar volume and I, okay? If we actually apply that particular case, we can link osmotic pressure with a free energy. I didn't show all the details, but if you do it properly, you will reach to this relationship. A2 is equal to 0.5 or 1.5 minus chi multiplied by unit volume of what is molecular 2 or polymer, in this case solvents, and molecular weights square. So we know that Seda condition is met when A2 equals to 0. Equivalently, we can see from this relationship, when chi equals to 0.5, A2 would be equals to 0, right? 0.5 minus 0.5 would be equal to 0. So that says when we have a chi equal to 0.5, we're going to reach a Seda solvent condition as well. Okay? So if everybody remember what is the significance of chi equal to different values, we talked about chi equal to 0, means there's no thermal exchange between your polymers. So chi equal to 0.5 means there is some negative effect for the polymer to be presented in solvent. Okay? The negative effect will be reflected in where? In this is where when chi equals to 0.5, you're going to start to have lower the value of your chain expansion because you're in a not so good solvent. That also makes sense here. In a good solvent, your chi will be equals to a negative value, okay? So that's how, generally speaking, you can use 0.5 minus chi to get a relationship between A2 and the chi value. So if it's a good solvent, we know this is going to be a positive value. That means chi will need to be less than 0.5. Okay? If it's a bad solvent, that we know A2 is a negative value, right? Say that solvent is 0. A bad solvent means A2 going to be negative value. That means your chi will need to be bigger than 0.5. Okay? This here is an example how we can show you can use the real experimental data to compute what's the molecular weight. So here is just an example. You can measure, prepare the polymer at different concentration. You can measure the osmotic pressure, you know what the gas constant and temperature is. You can actually plot this particular curve. Pay attention that we're not plotting osmotic pressure directly with the concentration. We need to plot osmotic pressure divided by concentration and RT, okay? Here the value C is important. If you don't plot osmotic pressure multiplied by C, you wouldn't get a linear curve. Only if you plot osmotic pressure divided by CRT, as we talked about in the last few lectures, you can get a linear relation. You can get the intercept. This is inverse of molecular weight. That's basically your A2 value right here, equals to 0.0001, which is equivalent, almost let's say the solvent in this particular case, in this example. I'll show again, remind everybody. That's why you need to plot divided by CRT, okay? That's the example how we can use that. So now let's move on. After we understand the chi A2 relation, we're going to talk about the phase diagram. What is the phase diagram and what is phase behavior? Let's talk a few science cases. What do we mean by that? So if you look at here, we can think about a few cases when the system is unstable, metastable, or stable. So what do we mean by different stable states, okay? And let's use eraser as an example. So we can show a few examples like that. In common sense, what we are trying to show is if you look at energy potential with different angle, what our bricks are, you can reach different energy state for the system. What do I mean? Let's see if this is strong enough to support. So if we have a table, we could have laid our eraser different ways to it. Oh, that's what I mean by metastable. And this is a stable. And this is unstable. If I let it go, it will drop. So that applies to phase diagram as well. It's a universal phenomenon that the system always going to relax to the lowest possible energy. What I mean by lowest possible energy is whenever there's a pathway to relax down to the lower energy state, it will be happy to do so. So think about here, you have a piece of rock. This is a mountain. It will be happy to roll down to the valley. If it stays here, will it be happy? Depends. Depends on, if I show this one again. Let me see if I can manage to stabilize. If I give it a little bit of shake, it's actually go back to where it's supposed to be, which is standing up. But if I shake it really strong, it will drop. You can also understand from this particular curve that just a little bit, it will be able to relax back to where it's supposed to be. So it is metastable. Unless there's a huge changes in the system energy, such as you give it thermal energy, it will have more kinetic capability to overcome here, then it can lower down here, okay? So this basically defines different states. Unstable is any perturbation will lead to the brick to fall to a more stable states, which is shown there. Metastable means any small changes that will lead to higher potential energy, okay? What do I mean by that? If I move it to left or right, it will go into the high energy states, and this will result in to relax back. Stable, this is we also call equilibrium or the ground states of the brick. Ground states means lowest possible energy. It will give enough time, the system will find this states. So for polymer blends, we are actually dealing with similar problems. Is if we, let's use the example of mixture, of if you're trying to mix a polystyrene in hexane, what is the lowest possible states it could adopt? So it will try to choose different configuration in the system, such as will I be more happier if I phase separate? If you have a layer of polystyrene, a layer of hexane will be lower in the system energy. And how this depends on, for example, perturbation, which means disturbance in the system's energy, will also reflect a role there. Okay? So let's go into the data and look at a few examples. We're going to discuss this typical figure. In the last figure, we plot system energy versus different states, right? Remember? But in this plot, it's a very common phase diagram for a material. In this case, we are actually talking about binary blends phase diagram. And what is a phase diagram and how do you read it? Not that hard. Phase diagram in this particular case is plotted as this. X is as temperature. Okay, so usually a lower temperature is at bottom, higher temperature is top. So you can think about, use examples here, such as this is room temperature, this goes to 50, this is hundreds of degrees Celsius. So higher temperature means higher in the region. And what is phi 2? Phi 2 we talked about. That's a volume fraction of your polymer in the blends. All right, so how much your polymer put in the system. And on the left, that means you have purely solvents. So that's 0% of your polymer. On the far right, your phi cannot be above 100% or 1. So phi 2 can reach only that high. Okay? Does that make sense, everybody? So now it's the interesting part. I give you a polystyrene. I give you a hexane. I ask you to mix them at a given temperature. And now how do we use a phase diagram to help you? First, I know how much solvent I put into the polymer, right? If I knew these two properties, I should get a value of phi 2. Let's say I put an equal volume of polystyrene and equal volume of hexane. So we should reach a phi 2 roughly in the center. Now I need to know another parameter, which is temperature. If I do this at room temperature, toluene hexane may not be a good example because they don't phase separate. But let's assume this is another polymer that would not dissolve well. 50% room temperature, you are going here, and this assumed room temperature, you will locate your data point at right here. And how you read this phase diagram is look at here. Is that in this region there is two phase. Two phase means it will not adopt a single phase, it will phase separate, okay? And so your polymer, you can understand they will not dissolve. in this particular region. I will talk about the gray region just in a second. It's a special phenomenon. They actually called metastable states, like the brick I showed vertically. They will dissolve, but they will not be stable over time. How about outside this area? So anything from here to this part, we call it a one phase. That means you can easily dissolve them, and it will not phase separate. That happens when you mix, put a little bit of polymer in solution, or at a higher temperature when you have 50-50%. So it will be one phase. It's kind of something people observe, that temperature for several polymers, when you heat them up, they improve the solubility. Okay, so this is what we show in this curve, but there's a couple curves we want to show. The first is what do we call spinodal curve. Okay, spinodal curve specifically shows this dashed line. This dashed line it's a special name, spinodal. But basically it says this defines the boundary between the metastable to phase separated phase, okay? Or metastable to unstable region. Any system falls within the spinodal region will undergo spontaneously liquid-liquid phase separation through the sample. Okay, so it will phase separate. Metastable is defined by the boundary between the binodal curve, this black one, and spinodal curve. Anything in between is metastable states. So what this says is it can phase separate, but it don't have enough energy to do it. If you put a nuclei, it will nucleate and phase separate. It needs some driving force to make that happen, or catalyst, okay? For example, in the eraser's case, the driving force would be I need to push it to above a certain perturbation range. All right, so that's defines metastable. And stable region is where outside this binodal curve. But there's also an interesting point. It's called critical point. Is defined by this green dots, or TC. This critical point defines above this critical temperature, above, okay? When you go higher than that, you always reach a single phase. The TC is relevant to the last possible, two phase you could have. So above critical points, you always reaches a well-dissolved polymer. I'll tell you a bit more how to construct a curve like this based on Flory-Hagen theory. Okay, this is again already predicted curve. So if I got this data for my polymer, my solvents, I would be able to make a better judgment how to engineer a solution so that they can be dissolved, or if I want to make a composite, will they phase separate or not. So how do we actually get to this curve is a question. This is a question about giving you a fish or teaching you how to fish. If I give you a phase diagram, you can probably solve this one problem. But if I teach you how to make this a phase diagram, you can learn how to do it for other polymers. Okay, next one. What we have talked about is actually what you show here. In this case, it's one phase. In the dashed, it's phase separated example. This is called UCST. Let me explain what each letter stands for in this acronym. U means upper. UPPER, upper. C is critical. It's slipping over. S, I think, is stable. Oh, man, it's slipping off my mind. UCST, what is it? Solution temperature. Okay, T is temperature for sure. S is solution. LC, this means lower, okay? L means lower. That means if you look at here, there's a lower tipping point. LCST means lower critical temperature, lower critical solution temperature, okay? Those are the difference between these two. And we're going to have some funky ones, but they're less common. And for example, here, you have to have phase separation, only have middle of the temperature. If it's too low or too high, they would choose to phase separate as well. Less common, okay? Similarly, you have some of the polymer with a phase separate only in the middle of their phase diagram, or in this case, they just don't like to phase separate if they phase mix if they have a critical range that it doesn't phase mix. The bottom ones are less common. Of course, you would also have, if something is always favors mixing, then you don't have a two-phase. You always are going to have one phase, no matter what temperature, what solvent you put there. So what actually potentially could cause upper critical solution temperature, UCST? So when we change the temperature, what are we actually changing here? The energy in the system. But if we think about the Flory-Hagen theory, right? We're talking about the driving force for the system to mix or not is defined by delta G. So the temperature will impact two things. First, it will impact the contribution of entropy, because delta G is defined by delta H minus delta S multiplied by T. So there is an influence there. Additionally, some of you might remember when we defined the chi. Chi is also dependent on temperature, although depends on what the definition of that. It will be A plus B divided by T, right? That's another way we can modulate temperature. So that's why combining these factors, we could get all kind of phase diagram looking at here. But for most of you, focusing on these two cases where these are most common, okay? And how do we determine the phase behavior? So if you're phase separated, how do we define it? And how do we experimentally measure it? So in these slides, we're going to show a few examples how people actually measure them. So when you have two materials, if they're phase mixed versus phase separated, the difference are in the phase mixed, they typically mixed at molecular level, and they could be homogeneously to your eye. But if you have high resolution capability, you can tell the difference. But for phase separation, that depends on what's the phase separation size. It can go from a few nanometer up to a few hundreds of nanometer or a few microns. But the system will always trying to minimize the contact area. So a lot of time you will see phase separation goes higher and higher over time if they're not frozen, right? So example is if you mix water and oil, if you shake it and sonicate and you create a metastable phase, they could be dispersed, such as a great example actually is milk. Every day you drink it, it's a mixture of oil within liquid. It's kind of stabilized, but it's look at turbid and non-transparent. So a good way to quantify the phase separation actually just using a microscope or measure the transparency of your down. If they're perfectly mixed, you tend to have normalized better transmission. Okay, all the light just goes through. Once they phase separate, those droplets formed actually has the ability to scatter the light. So when you shine a light through it, it not just transmit, but it's also going to be banded and scattered in different direction. Okay. So in the next year, you guys will do a lab called light scattering experiment. You will see when you have lots of particles there, it's much easier to scatter lights one side away. So here, what it shows is this is an example of showing you if we mix two materials at different concentration, when we go through this particular temperature, we can get what is the phase behavior. So you can assume when transmission is low, that means it's a phase separate. So you can see when you load more materials, more polymers in terms of concentration, this goes up, but the critical phase separated temperature goes inversely, okay? If you have just put a little bit of polymer, even at high temperature, will be stable. So this basically is a UCST or LCST behavior, everybody? When we heat up, it phase separate. No, LCST. LCST, right? At low temperature, it's happy. When you heat up, it's phase separate, beam turbid. So it's actually followed here. And when you look at when we put a little bit of material, we need to heat to higher temperature to have cross this phase boundary. If we load more and more, the curve we basically shows you if I have a few percent to 5 to 10%, we're going to drop in the temperature transition from one phase to double phase. This is how we typically measure them. So now the question is, how do we get their phase diagram? How do we go from a Flory-Huggins theory to a phase diagram? This is a little bit tricky question. Anyone can help me? Phase diagram, Flory-Huggins theory. In appearance, this curve is very relevant, okay? So first, let's take a look what is this curve. This curve is plot again. Don't be confused when we talk about phase diagram, because this now shows what? Delta G mixing. And this shows what chi2, what is x2. X2 is number fraction for the polymer, or the second component in the mixture. So how can we get this curve? Anyone knows? How can we get this flat curve first? Oh, come on. This isn't that hard.
Try different number fractions.
Yes. So everybody still remember what is a Flory-Huggins equation or lattice theory based on delta G? Delta G equals to x1 log x1 plus x2 log x2 plus x1 x2 chi. If you know what is the chi value, you can get this curve, right? Because the only thing I know is basically x1, x2, and this x1, x2 is defined by here. At the low value and the high value, so in this example, when this is delta G, okay? And what do I mean by these two data points? Okay, so this is the data points in the delta G value. So let's assume this is going to be, you prepared a polymer at this concentration at 2, x2. Will it be stable? Will be stable. Will be it stable. So I'm going to use this again. Will be it stable depends on if it can handle a tiny fluctuation in the solvents. What I mean tiny fluctuation, because those polymer chains are fluctuating in the solvent. What I mean fluctuating is they're moving along. If you take an average of the whole beaker, you know how much concentration are. But if you have a magnifying glass, you can zoom in bigger and bigger, then you can hit a region that is no polymer chain, and polymer chain would swing to your swimming pool and get out. Pretty much like how many population in this town over a year is relatively stable, but if you look at a given time, in summertime, in wintertime, people might come in and go, right? So same here. Now the question is, when you have a chain going in and out, will the system prefers it to be phase separate or not? Will depend on this. So if the chain happens to be diffused out, what happens in the local population? Local population in that solution will drop. And the chain cannot disappear, so it's going to go into the other area. So you basically, this particular will happen. Will they split? Or will they be joined back to their original states? How do we understand if that's possible or not? As we are talking about thermodynamics, so everything can be understood as the delta G. So this curve shows you, we know what is delta G at when we start with M at this concentration, X2. Do we know what's the delta G when we have phase separate in XA? Yes, we know. You can put in and calculate what the XA is. Do we know XB is? Yes. And we also know there's conservation of mass. You can't create more of XB without sacrificing the XA, because the total amount, like I said, if I have 10 mix per mil, I cannot phase separate into 13 mix per mil and 11 mix per mil, because I could not create new material from nowhere. So this curve basically shows you, if phase separation indeed happens, what would be the new delta G? When I'm combining those two energy state linearly, so this basically is the new energy for the combined system. Okay, let me repeat it one more time. I got a 10 mix per mil beaker of toluene dissolved in hexane. Now I can create a new beaker that is half a volume, that is 7 mix, and the other beaker is 13 mix. So now I need to consider which system has lower energy. Is it 10 mil of 10 mix or other 5 mil of 7 mix plus 5 mil of 13 mix? In this case, it shows the other split system has a higher energy as we can linearly combine them. So what's system going to do? It was, oh no, I don't want to be separated. I will be happily rejoin and lower my system energy from this to here. Okay? This is how we can define if the system would adopt a phase separation based on Fourier-Hagen theory or lattice theory. They're basically very similar. We just need to consider the phase separation energy. So, this happens for other combinations. You can say, what if I want to phase separate into 0 and here? Some of my material will be purely solvents. Some of them will, again, you will look at the same. I could not find any two data points on this curve will be, linear combination will be lower than this. Because this curve is, if you look at this parabolic curve, it's concaved up. If you have a concaved up parabolic curve, you will never be able to find a phase separate system where we have lower energy. Okay? This one, I believe we touched a little bit already. So example of, we can have phase separation, assuming 10 mix per mil would phase separate into a low concentration and high concentration region. And you can combine what is total free energy and compare in the mixed state and versus phase separate states. The same statement as I just argued to you. Considering conservation of the mass, because after you phase separate, you don't create a new material. Okay? So, how about in this case, if I now have a delta G locally is now forming a different shape. It's concave down. Now it's a different story, right? So how it different with the last one is now, if I make the same argument, if I have a 10 mg per mole material, it phase separated into a low concentration and high concentration. When we consider after phase separation, it will have a lower system energy compared to where we start off. What will this polymer do? It will choose to stay phase separated phase. So your system will turn into, if there's density difference in polymer, so you're going to have a dense layer settled at the bottom of your liquids, and you're going to have something separate at the top of it. You will form two layers with over time goes on. Okay? So now the question is, if we want to define a phase diagram, we need to decide locally how does delta G depends on phi value, right? If we know what the delta G depends on phi, we know this is unstable states, the other is stable states. Unstable will phase separate into two, stable will stay. So we can construct the phase diagram. So let's take a look at different contributions. Revisit what is the lattice theory. Okay, we know this is the entropy contribution, chi contribution, right? So let's look at the first. We know delta S is always going to favor the mixing because it's always going to be taking a negative value. But now let's dive a little bit deeper. If we plot what is x1, we can see at a different blend ratio, it will follow this parabolic curve. When delta H, when H is a positive value, it will also take this shape. Okay, when you combine those two, the delta G will adopt the different shape. Now, if we look at different chi value, now this is interesting. When you have different chi value, now you can have different relative contribution between the delta S and delta H. When chi equals to 0, when we put in different x1, x2, remember, equals to 1 minus x1 is always going to be flat. But if you have now chi equals a positive value, this is what you will have. Now, next step, let's combine delta G with delta H and delta S. Now things getting interesting. What's so interesting?
Looks like we have a that is stable.
Then you can see at chi equal to 0, it's always going to be a delta G dependence on x1. It's always going to be stable, right? But when you have, like our student said, when you have chi goes up, you now start to see chi makes a bigger impact, and you start to see a different region. In this region, your delta G is concave down, but in this local region, it is concave up. So you're going to start to see interesting phenomena in phase diagram. And let's analyze it and understand a bit more. How does chi impact the phase diagram? So for this is actually for regular solution theory because the delta S is symmetric, right? So, but in Flory-Huggins theory, it will be slightly different. That's what we show here because delta G of mixing will have less contribution from the polymer part. So the phase diagram will be smeared to one direction. It will no longer be symmetric. This is because of the normalization factor from this end. Okay? But for the simplicity, let's first take a look at the phase diagram. from the solution only. Let's first skip these slides. What is phi value? If you plot in, you will be able to get this curve. It may not look like this as we show. Some of the real data might look a little bit more complex depending on what is. This is in case of polymer mixing, right? So if delta entropy contribution is more complex, it have a discounted factor N1, N2, which is dP for polymer A and polymer B, and chi N. So your phase diagram, delta G versus X1, will look very different. So what is mean by locally stable? So this is the last part we're going to cover today. So this is again is a deviation in concentration. It's like what I mentioned to you. When we have a liquid of polymer, the polymer chain will move around, so it will have deviation in concentration at different position. In this classroom, everybody is sitting always at the same seat, but if you think about me as a polymer and the stage is your solution, it's pretty realistic, right? Because the solution volume fraction, let's say you dissolve 1 mg per ml, you have about 0.1% of polymer by volume in there. So, 1 out of a solid space available. I like a polymer chain. At the solution, I like to move around. Nothing frozen me staying there in solution, right? So at a given time, where I am standing has a higher concentration of Dr. Gu compared to there. It will fluctuate over time. But if you take average, over the classroom, I have average concentration is defined by how many me and how big a space. But locally, at a given time snapshot, you will have this concentration. So phase behavior is basically said if this concentration fluctuation will cause permanent damage or it's just temporary. If it's temporary, the system will relax to where it original is, which means I'm going to walk around, but I'm always going to be confined in the area. I'm pretty happy. If it's metastable, that means if you create a system, if I walk around, I found a place that I'm pretty happy, then more and more of similar, let's assume there's more molecular in this system. So all the students come, get closer in the corner, then we have a spontaneous phase separation. We get half a layer of more polymer if fluctuation is preferred. So that's what this slide means. And if the fluctuation is a fluctuation in concentration, give rise to a better, a lower overall system energy, the system will prefer to stay there, and it will stay there for a long time. That's what defines if your system wants to be one phase or two phase. Okay, so the phase diagram we showed at the beginning comes from the delta G versus the phi plot. In next class, we're going to go from how actually we go from delta G versus phi to the phase diagram. So we're going to show how you can link this curve, delta Gn, to the phase diagram curve, which shows blue. Okay? So any question for me for today's class? If not, then feel free to shoot me an email. If you have questions, what's the link between Flory-Hagen theory, lattice theory versus phase diagram, part 1. In the part 2, we're going to catch up the rest of it. Okay? With that, let's finish today's class.